So let's begin with the chapter of vectors. Vectors is actually a subject of maths. So why are we studying it in physics? So to understand that, first let's understand why do we even need maths in physics. So just like how the brush is important to a painter, similarly maths is important to a physicist. Just like a painter, he cannot paint without a brush. Similarly, a physicist cannot do physics without math. Even in your earlier classes, you would have used some of the maths in doing the physics, consciously or unconsciously. For example, when planet is revolving around the sun in a circular motion, when we say that, or when we say that angle of incidence is equal to angle of reflection, or when we say S is equal to ut plus half at square. So all these equations, these angles, these lines, these circles, these are all mathematical terms. So we use it in physics. In your earlier classes, you have studied of certain branches of maths. For example, algebra and geometry, trigonometry, arithmetic, etc. So for these higher studies, since we are now studying about the physics at the deeper level, we will also need maths of a certain advanced level. So now we are going to introduce two new chapters or sections of mathematics, vectors and calculus. So we'll begin with the vectors in this chapter. Later on, we will study a bit about the calculus. You will study the calculus in detail in your later classes. For now, let's study about the vectors. So before we get into the vectors, let's understand this term of physical quantity. So any quantity that can be measured, like mass or volume or temperature or length, all these are physical quantities. So there can be more, like density, velocity, speed. All these are physical quantities. Now some of these physical quantities need a direction to define them completely. For example, there is a ball at the top of the cliff and we apply a force F on it. So if we apply the force in this direction, or we apply it in this direction, or we apply that force in this direction. So and we need to tell that this ball will fall on the A side or the B side. So clearly in the first case the ball will fall on the B side. In the second case it falls on the A side. And in the third case it does not fall at all. So what is the difference between these three cases is the direction of the force. We can see that the same force is applied in all three cases, but the direction makes all the difference that where the ball will eventually go. So force is a physical quantity that needs direction to be defined completely. You cannot just say that there is a force F and the ball will go in a certain direction. You also need to tell in which direction the force is applied. Now there are some other physical quantities that do not need direction. For example, temperature. It does not need direction. You don't say that this temperature is 20 degree north or 20 degree south or east or mass, for example. So these physical quantities don't need direction. And some other physical quantities like velocity and displacement are the ones which need direction. So now we can clearly clearly bifurcate all these physical quantities into two, which need direction and which don't need direction. So those physical quantities that need direction to define themselves completely, we call them vectors. Those which do not need direction, we call them scalar. So we can write some examples of vectors as velocity and force, and example of scalar as mass, temperature or volume. So now let's talk about the representation of vectors. So there are certain ways vectors can be represented. So let's discuss them one by one. Number one is by symbol. So when we say that the temperature of a body is 2 degrees centigrade, right? So let's say it's represented by symbol A. So we say A is equal to 2 degrees centigrade. Or when we say volume of water, B is equal to 25 meter cube. So these are the symbols we are using to represent the temperature and the volume. Similarly, for the vectors, let's say we say that the velocity is 5 meter per second towards right. So we represent it by a symbol C. Or let's say we say the force D is equal to 10 Newton towards north. Now we can see that there's no way from just seeing the symbol we know that the quantity is a scalar or a vector. So what we do is we put an arrow on top of these symbols so that we immediately know that we are talking about a vector. So this is similar to when we see a policeman which is wearing his uniform. We immediately know that that man who is wearing that uniform is a policeman. Similarly, when we see an arrow on top of these symbols, we immediately know that we are talking about the vector. Now here it is important to note that this force can be in this direction or it can be in this direction, but in both cases when we are talking about the symbol, so this is A, and for this force let's say it is B. So in both cases the direction of the arrow is going to be from left to right on the top of the symbol. For this you cannot write that the vector is like this is wrong. Or if the force is in this direction, you don't write it as this is also wrong. So this is the only correct way of representing a vector. So this arrow is just a representation. It does not show the actual direction of the vector. So for the direction you need to write always. So you can say that F vector is equal to, let's say, 10 Newton towards north, or it is velocity is equal to 20 meter per second towards south. So this direction of the arrow has nothing to do with the actual direction of the vector. So here we can also say that every vector has two components. One is the magnitude, which in this case is 20 meter per second, and another is the direction. In this case it is south. So this magnitude we can also represent by this symbol. So now let's talk about the second way to represent. So this is the second way a vector can be represented. It's by arrow. So let's talk about the force. This is a vector and I mark it as 20 Newton. So this arrow represents that the force is in the direction of east, and the size of the arrow relatively explains you what is the magnitude of that force. So for example, this arrow means 10 Newton, or this arrow means 30 Newton. So the size of the arrow represents the magnitude of the vector, and the direction of the arrow represents the direction of the vector. So in every representation of the vector, you will see the magnitude and the direction being represented in a certain way. So let's say if the need not be necessarily in the right. So this is the v is equal to 5 meter per second. So this vector again can be broken into the magnitude and direction. So magnitude is 5 meter per second and direction is in this direction. Or if it is 2 meter per second, so again its magnitude is 2 meter per second and direction is in this direction. So in the representation by arrow, this is a tail. This is called the tail part of the vector, and this is called the head part of the vector. So sometimes we also write it as, if this is A and this is B, instead of writing as V vector, we write it as AB vector. So then we can write that AB vector is 10 meter per second towards right. So A is always for the tail and B is always the head. Now let us talk about some new physical quantities. Let's start with the position. So these new physical quantities which we are talking about are vectors. So position is a vector. So let's discuss about it. So position means simply where an object is located. So in this statue example which we did, so this is a statue at the center and our house is here. So if someone asks the direction about where the house is, you can say that this house is 20 meters north of statue. So here in this position vector, again every vector you will see that it has a magnitude and a direction. So the magnitude is 20 meter per second and direction is north. Now can we say that position of the house is just 20 meters from the statue? No, we cannot say that, because then that means this house can be anywhere on this circle. All these points on the circle are 20 meters from the statue. So in itself 20 meters is not enough to define a position of an object. We need a direction as well. So since we need both the magnitude and the direction, we can say position is a vector quantity. Now we saw in the previous example that we needed a certain reference point in order to tell where the position of that house was. We said that it is 20 meters north of statue. If we don't tell the statue, or so we cannot say that it's 20 meters north of what. So we still won't be able to reach this house if we don't mention the word statue. So in this case, this statue is a reference point. So this is a general example from a real life, but such references points are needed to define the position vector, and that's where we need the coordinate system. So to know the position of an object precisely, we need an origin. Here the statue can be called the origin. So here we normally take the reference point as origin in a coordinate system. So now if an object is, let's say if it is in the same case, this house is here, we say A is 20 meter north of origin. Or if we have an object B at 30 degree with the positive x-axis, we'll say B is, let's say this is 70 meter, B is 70 meter at 30 degree from origin, from positive x-axis. So this 30 degree from positive x-axis, so this is your positive x-axis, and when we say just 30, it's positive 30. So this is the direction. So 70 meter, this is the magnitude. To define, so all this is for the position vector. So to define a position vector, we need a reference point, which is in this case is origin in our coordinate system, and then we say the magnitude and the direction. So now we exactly know precisely that with respect to our reference point, in this case origin, where is the object located. So in this example, let's write the position vector of all these points. Also, position vector is represented by a symbol R. So in this case, position vector, you can try it for yourself also. So we can say that position vector of A, so we can represent it as RA, is, let's say this is 10 meter, so 10 meter along positive y-axis. So this is x-axis, this is y-axis. So our B vector is 20 meter at 60 degree from positive x-axis. So this is at 60 degree from positive x-axis. Position vector of C is equal to 30 meter at 30 degree from positive x-axis. Position vector of D is equal to 20 meter along positive x-axis. Position vector of E, so this one is making 45 degree from the positive x-axis in a negative direction. So we can say it as 10 meter at minus 45 degree from positive x-axis. So all these are the position vectors of the points A, B, C, D, E, which we are representing with this reference frame, which is our coordinate system. So clearly, if the coordinate system was different, if the coordinate system was here, all these position vectors will be different now. So RA will become, instead of 10, it will become probably 50 meter in some 75 degree from positive x-axis. So when we are talking about with respect to the new origin, so position vector of A is equal to 75 meter at, let's say, 80 degree from positive x-axis. So you can clearly see that the position vector depends on the choice of the origin and coordinate axis. So if the origin is same but your coordinate axis are in this direction, if I take this as x and this as y, again my position vector will change. So position vector depends on the choice of the origin and the coordinate axis. Now let's talk about another physical quantity, distance. So let's define distance as the length of the path traveled. So distance is a scalar quantity. Let's say if a cab, you can think of it as a cab which you are taking from and going to point A to point B. The cab driver will charge you for the length of the path he has taken in order to reach the point B. So this distance, let's say, is 200 meters, this path length. So we'll say distance is 200 meters. Even though if you join the point A and B directly, this distance might be just 100 meters, but we'll say distance is the length of the path covered. Which brings us to our next physical quantity, displacement. So in this above example, if we directly connect the point A to the point B and we see that in which direction and which magnitude eventually the cab goes, that will be called as displacement. So here we are talking about the magnitude, which is 100 meter, and this direction. So let's say this is 30 degree. So 100 meter at minus 30 degree from positive x axis, assuming that point A itself is origin. So we'll say displacement of this object, this cab, is 100 meter at minus 30 degree from positive x-axis. Again, this is the magnitude and this is the direction. Now it is interesting to note that between point A to B, you can reach point A to B in many number of paths. You can reach it in paths which may have different distance or even the same distance. So let's say this is 200 meter, this is 400 meter, and this is again 200 meter. So all these paths are different, but their distance can be same or cannot be same. But the displacement, eventual displacement when you are reaching from point A to B, is always 100 meter. So when you reach from a point A to B, it does not matter what path you take, your eventual displacement is always same. Now let's take an example of a boy who is running in a stadium from point A, or he is doing his football warm up before his match begins. So he's going into the circle and his instructor asked him to run around the circle 4 times. So in his 4 rounds, what will be the eventual distance which he travels? It will be 2 pi r times 4. What will be the displacement after the 4 rounds? It will be 0, since he comes back to the same point. So essentially he did not displace, even though the distance covered is 2 pi r into 4. Now, even if it is 16 rounds, then the distance will be 16 times 2 pi r, but displacement will still be 0. So now let's do this example. This is the coordinate system. This is positive x and this is positive y. Let's say the object travels from point A to point B. Right? So what will be the displacement in this case? Clearly, displacement is AB vector. But now let's relate displacement to position vector. So relating position vector with displacement. So what is the position vector of RA? It is like this. Let me use some different color. And position vector of B is RB. So if this is 30 degree, this is 60 degree, and let's say this is 45 degree. So now for your exercise, write down what is RA vector, what is RB vector, and what is the displacement, which is AB vector. If it is given, this is 10 meter, this is 20 meter, and this is 15 meter. So just try it for yourself. So I hope you have tried it. Now, so our A vector in this case is 10 meters at 60 degree from positive x-axis. Our B vector is 20 meters at 30 degree from positive x-axis. AB vector, which is the displacement, is 15 meter at minus 45 degree from positive x-axis. So in this example, you can see that the displacement vector AB vector is the line joining the initial and the final position vectors. So the position vector of the head of the position vector RA was here, RB was here. So the line joining the end of the RF final position minus RA initial position is the displacement vector. We'll study about this later when we will talk about subtraction of vectors. So let's summarize what we have. So there are physical quantities like mass and volume, which only need magnitude to define themselves. So these physical quantities are called scalars. And there are some other physical quantities like velocity and force, which need magnitude as well as direction to be defined. So they are called vectors. So their vectors can be represented by either a symbol, in this case a variable with an arrow on top of it. So we can write as V vector is equal to 20 meter per second north, or we can represent it with just an arrow. So when we mark an arrow at right 20 meter per second, we don't need to specify direction, because the direction of the arrow itself specifies which direction this vector is in. Now we talked about these three physical quantities: position, distance, and displacement. It's important to know the difference between these three. So position is where the particle is at a certain instant. So it needs a coordinate system to define where it is. So it needs a reference point in our coordinate system. The reference point is origin. It's represented by the symbol R vector. Distance is the length of the path traveled, and displacement is the line joining initial and final position vectors. Now let's do one example before we will move on to the next chapter. Not next chapter, the next section of the vectors. So in this example, we have a coordinate system. Let's say the particle travels from point A to point B on this blue path. All the values are given. Now what you need to do is indicate Ri on the graph, indicate Rf on the graph, calculate distance, and tell what is the displacement of the particle. So try this in your notebook and then see the solution. So in this case, the Ri is when we just connect the origin to the where it starts. This is the Ra vector. Rf is again the line joining the final position to the origin. This is the position vector, the final position vector, Rf vector. Distance, length of the path. So this distance plus this distance. So in this case, this becomes 4 plus 2 pi r is 2 divided by 4. So 1/4 the complete circumference of the circle. Displacement is simply the line joining the initial to final position. So remember that in this case it may look like this is the displacement, but no, in this case the displacement is the line joining the initial and final position vectors. So it is AB vector. So displacement AB vector is equal to, if this is 2, this is 2, this is 2 root 2 towards at, this is 45 degree by Pythagoras theorem. So it is 2 root 2 at minus 45 degree from positive x axis. So this is the answer.